I think we have enough. Let's begin. Today we will continue with our discussion on deriving the full gas dynamics equations and the Navier-Stokes equation. So I was thinking about the purpose of this derivation. I want you to understand. I want you to understand what's going on. It's a difficult derivation. It took centuries to figure out all of this, right? But I want you to at least understand what the terms mean, how we obtained them, the process of obtaining them, because it will require practice to know how to do that by heart or directly kind of from your mind. So my expectation for you in the exam is for you to just know how the terms came about. Like if I ask you about the advective flux or later on the diffusive flux or what's a surface force, right? So just to know how those pieces fit together, because it's a lot and I get it. And frankly, you need to see this over and over again for it to really sink in. Now, for your exam, you will also be given the full equation sheet, okay, in different forms and different coordinates. And I did upload that on Canvas under supplementary materials. And I will send an announcement about that. So you'll have the full set of equations. You'll be able to just use them as needed to obtain solutions. So this is not so much about the derivation itself, although that's important because that's where creativity comes in, right? What are we doing here? But it's about the more of the mechanics of how we worked on this and an opportunity to introduce tensors and tensor calculus. And again, for tensors, you need to just know about them just enough to be able to operate with the few things on tensors. But that's it. Once we work with the equation set, we will be working with individual equations in X mom, Y mom, Z mom separately, right? You're not doing fancy additional derivations on Navier-Stokes where you need to work with the full set of equations in tensor form. And so if you're doing research in modeling, for example, in fluid mechanics, you would need to do that. Otherwise, I'm not trying to lower the standard, be careful. So what I'm trying to say is, it's a pragmatic perspective on what these equations are, what they mean, and why we are doing this and what we want from these equations, okay? So I'll summarize, I'll pick up where we left off last time, if I can find my annotator. Okay, there's the annotator. So last time we spent a considerable amount of time on the last lecture discussing the Reynolds transport theorem, which allowed us to move from a Lagrangian perspective, which is the perspective from fundamental laws of physics, where you draw the law as you are following the material system, okay? It's as if you are living in the material system. Things are only changing in time and you're looking at it as it evolves in time. But then we discussed that that's incredibly complicated for fluids because you would have to track a considerable number of fluid elements and track their deformations over time. It's incredibly expensive to compute, right? So then we argued that a cleaner perspective, an easier perspective, is the Eulerian perspective, where we fix a region in space and let those fluid elements pass through, and two things will happen. The fluid elements will bring in information to those control volumes. They will change the speed, the velocity, the density, the pressure inside those control volumes, or vice versa. Any change in the control volume will be inherited by the material element. It doesn't matter which is causing what. The point is, once we express the equations in that form, we are able to solve for those properties, the velocity, the density, the pressure, the temperature, etc., in those control volumes. Then any fluid element that goes through that control volume is going to inherit those values. So on the left-hand side here, you see that transformation from the Lagrangian to Eulerian, written for the three momentum components, momentum per unit volume, so rho u, rho v, and rho w, okay? And so that tells us the change in time, the accumulation or the depletion of x, y, or z momentum in a fixed control volume. Again, that control volume essentially is going to be a point on our grid when we do a numerical calculation, for example. The second one is the advective flux, and that tells us what these fluid elements are bringing in and taking out of that control volume. And always the flux it's either a surface integral or its equivalent, the divergence of some vector field, okay? And notice, pay attention to how I'm writing these. The advecting velocity, that's the full velocity vector field. And what is being advected? The advected information, rho u, rho v, and rho w. If you keep following that notation, it will simplify things for you. I know you might want to reorder things because mathematically it's more beautiful to write rho v and then vector u. But for the sake of this derivation, until you comprehend all of this, keep it in this form, okay, so that you can distinguish between the different components. And then finally, on the right-hand side, we had, so this is nothing more than Newton's second law. The rate of change of momentum is equal to a summation of external forces. And we were going to spend some time deriving these external forces. Last time we just did the gravitational force, and I will cover that again. But note that the external forces is a vector because the momentum itself is a vector, rho u, rho v, rho w. Here we separated it into individual components, rho u separately from rho v, from rho w, but the external force, it's a vector. The components of this vector, the first component corresponds to x momentum, so that's fx, or force vector dotted with the I direction, that corresponds to x momentum, and then y momentum and z momentum. Okay, good. Next, we talked about external forces, and we distinguish between two types of external forces: body forces, which act entirely on the entire volume of the material element, or the control volume. It doesn't matter. We don't need a reference change anymore because external forces, they're external. They apply equally to the control volume or the fluid element. And there are surface forces that act only on the surfaces of the control volume. And typical body forces are the gravity. That's the number one. There's magnetic forces as well. Those act on every point in the body. And so I gave the example that gravity is acting on every cell in your body, but the atmospheric pressure is acting only on the outer surface of the skin, essentially, of you. Okay? We start with gravity, and I said in general, there's a gravitational field there's acceleration essentially in all three directions. And you could have an accelerating frame, etc. So we would need to account for the different acceleration components. So in general, we write a gravitational acceleration vector field as gx, gy, and gz in the I, j, k directions. And the total force of gravity, we need to have consistent units, right? So this force of gravity needs to have units in Newton, right? So then we have rho g, which gives us Newton per unit volume, force per unit volume, and then multiplied by volume, that takes away the volume, and we get newtons, right? And so that's what we would need here, and then that gives us the separate components, rho gx and rho gy and rho gz in the individual directions. So this would be the x momentum contribution for the rho gx. The rho gy dv would give us the y momentum, and the rho gz gives us the z momentum contribution. I'm writing everything in terms of a volume integral because I am foreseeing what we did with the balance equation when we converted all integrals to volume integrals, and we said, well, the volume is arbitrary, so therefore the integrand must be equal to 0, and everything was in the same, written in volume integrals. That's what I'm headed towards, okay? So that's why I'm writing these as volume integrals. Even the surface forces, I'm going to convert them to volume integrals. Okay, so that would give us these individual contributions. We're going to add those up eventually. So the x gravitational force goes in x momentum, the y gravitational contribution goes to y momentum, and so on. Next is the next two forces are surface forces. The easier one is the pressure force, and the pressure is only a surface force. Remember, pressure is a scalar. It's just a number like temperature. Okay, it doesn't have direction. It doesn't make sense the temperature in that direction is this and the temperature in another direction is that. No, pressure is just a number. However, what's unique about pressure is that once you put a surface, once you put a metal piece or some volume, anything, suddenly that pressure starts compressing on that surface, okay? So that's what's so unique about pressure, although it's a scalar, but in the presence of a surface, it becomes a vector because it becomes a force. It's exerting, so think about it as if it's exerting weight on that surface, okay? Atmospheric pressure, it's exerting forces on all directions, right? And so, and I can prove to you that it exerts force in all directions. Put something lighter with a density that's lighter than water in water and push it down. It's gonna float up, Archimedes' principle. Now why? Because there are surface forces from the pressure being exerted on top of the object and at the bottom. It's just the forces at the bottom are a little higher than the forces at the top from the pressure. It's a purely pressure force. So pressure is acting on all surfaces, but it's always a compressive force. Okay, it's always trying to compress it. It's always trying to push it in. Now what ends up happening across the surface on the other side, whatever happens, if the force on the other side is a little bit lighter, then it's gonna go in that direction. If it's a little higher, and it's gonna go in the opposite direction, right? So what matters is that difference across the surface. The pressure is always a compressive force that acts on the surface of a fluid element or a controlled volume equally, it doesn't matter. And because it's a scalar, but in the presence of a surface it becomes a force, how do we turn that into a vector? The unit normal allows us to turn the pressure scalar into a force vector. Why? Because the pressure is a compressive force. It's acting always normally to the surface. So the unit normal tells us the direction of that normal normal force, right? And then that gives us that integral of minus p n outward unit normal ds. Now, because n is always pointing outward, if we were to put pn, then pn would always be pointing away from the surface, okay? Because the pressure is always greater than zero, unless we're not looking at relative pressure. It's zero or higher, right? So the pressure is a positive number. If you put pn and n is outward, then the pressure will always be outward, which is wrong. The pressure needs to be always pushing in. So that's why we put the negative sign, okay? That's why we put the negative sign to designate that the pressure is a compressive force. Okay, it's a normal compressive force. P is just a number, a scalar field. It changes in space, changes in time. Whenever you put a surface, it's gonna act on that surface. It is present everywhere in a fluid, and once a surface is defined, we have a unit normal, and therefore we have a pressure force. Now, when we integrate that integral, when we integrate over the entire surface, so remember, the pressure is force per unit area, right? To turn it into a force, we need to multiply by area. In other words, we're integrating. That's why we need that integral. We're summing up all that force per unit area times the little areas until we get the net force of the pressure. The net pressure force is a vector, and that vector has three components, I, J, and K, okay? So let me give you an example. Consider this conveniently rectangular element submerged in a pressure field, atmosphere or water, whatever. Okay? It has faces A, B, C, and D. Its thickness is delta Y and its length is delta X. All right. And I put here also the unit normals for the surfaces. So surface A is pointing, the unit normal is pointing in the minus I direction, while surface C is pointing in the plus I direction. This is a standard coordinate system, X, Y, plus I, and plus J pointing upward. So the D surface, the unit normal, is pointing plus J, and the B surface is pointing in minus J direction, the unit normal. Now, I'm also assigning a pressure field. At those surfaces, the pressure is going to be constant because I don't want to be dealing with integrals, just to simplify the analysis. But at the surface A, PA is 5. At surface B, PB is 5.2, just some arbitrary numbers. At C, the pressure is 6. And then at D, the pressure is 4.9. And that's just a number. Okay, it's just a number. Okay, it doesn't matter where you're looking at. It's just a number. It's equal everywhere on that surface. Okay. Now, if I wanted to compute F pressure, I need to evaluate the pressure force on that entire volume. Okay, on that entire volume. All right, because that volume is closed. The pressure is acting on it. Is gonna either push it up or down or sideways, right? And so I need to calculate that total pressure force vector. And that's the integral minus Pn ds. So let's split it out. Because this is a rectangular surface, it's easy. I'm going to sum up the integral on each one of those surfaces. So starting with A, it's minus Pn minus Pa. What is the unit normal on A? It's minus I. So I have minus Pa minus I dy. Now that's constant, so I can take that out, and that's going to be Pa times delta y, right? On surface B, I have minus Pb times the unit vector, not a dot product. This is a scalar. This is a scalar times the unit vector. So if the scalar is 2, it's going to be 2i or 2j, right? So it's minus Pb, and the unit vector is minus j. So I have minus Pb times minus j dx. Now Pb is constant and j is constant on that surface. We're going to pull them out, and you're going to get a delta x. Next, on surface C, I have minus Pc, but the unit normal is plus I. So I have minus Pci, and then the surface is simply delta y. It's unit in the z direction. And then finally, there's no depth into the plane. And finally, on surface D, it's minus Pd times the unit normal, which is plus j, right? And then you summarize that, you get two components, right? I and j. It's a pressure force vector. It's a vector. All right, the I component is Pa minus Pc times delta y, and the j component is Pb minus Pd times delta x. And therefore, the x momentum contribution in this case would be Pa minus Pc times delta y, and the y momentum contribution would be Pb minus Pd times delta x. Does this make sense? Just giving you a simple example. It's not magic. You did this in your homework assignment when you integrated over the cylinder. The pressure distribution doesn't have to be constant at all. Okay, that's why you have to integrate it. In this example, it was constant to simplify the integral. And I did some animations here to show you how the pressure force continually changes in a pressure field as the surface is changing, depending on the shape of your control volume or your fluid element, right? The forces, the pressure force is always normal and compressive. Okay, so if you were to compute, you needed to compute the pressure force on this object, you would have to do that entire integral. You would know the pressure field, you would know the unit normals, which is the hardest part, and then you would need to know everything about the surface so you can compute that pressure force. Okay, in both of these cases, the resultant force is a pressure vector. Okay, it's gonna determine where that object is gonna move. Now, working with surface integrals is cool because it's just kind of simple, pressure times n, but it's problematic in the sense that these surfaces, you need to know everything about the surface to be able to identify the individual components of the pressure force. A cleaner approach to give us, remember, I'm after the x mom, y mom, and z mom contributions of the pressure force, okay? And I'm after those. What is the I contribution? What is the j? What is the k contribution? A cleaner way to do this is to convert the surface integral into a volume integral using the gradient theorem. Because once I convert that into a volume integral, the gradient is immediately just giving me the I, j, and k components, whatever the surface is. This is the beauty of these integral formulas, okay, of these integral theorems. Now, moving from the surface integral to the volume integral, I no longer need to know what the surface looks like, because the gradient is just giving me automatically the x, y, and z components. What are they? Well, grad P is dp dxi, dp dyj, dp dzk. Done. Those are the components of the pressure force, okay? So if you split that out, the gradient is minus dp dxi, minus dp dyj, minus dp dzk. You still have the volume integral. You need to integrate over the volume. We're going to get rid of the volume later, of the volume integral. But it automatically gave me the x, y, and z mom contributions, right? So that's my x mom contribution, that's my y mom contribution, that's my z mom contribution. If we were working with the surface integral form, we would have to know what the unit normal is. Then you might say, well, if we do it on a cubical control volume, yes, you'll be able to do that, and you have to shrink it infinitesimally to get derivatives. This is cleaner. The integral form does that for you in one shot, okay? So that gives us the pressure force. And again, to stress the fact that the x component of the pressure force is the pressure force vector dotted with I. So that's going to give me my x momentum contribution. The y momentum contribution is the y component of the pressure force, which is F pressure vector dot pressure force vector dotted with J, and that gives me that integral minus dp dy dv and so on. Now notice what matters here in that pressure force from the volumetric form. What matters is not the values of the pressure on either side of the surfaces. What matters is just the gradient between across the volume. What matters is just the gradient, not the values of the forces themselves. You could have a value on one side that's 1,000 newtons per square meter, that's 1,000 newtons, and on the right that's 500 newtons. That's the same as having 500 and 0, or 750 and 250. So the values of the pressure themselves don't matter. It's the gradient or the difference across the surface of the volume. Okay, and that was apparent if you go to this example. If you notice, the x component of the pressure was the difference in pressures across delta x and the difference in pressures across delta y, right? So it's that difference that matters, all right? It's that difference that matters because pressure is acting on all sides. So the net component is the difference between the sides, okay? Any concerns, any comments, anything not clear here before we move on? Okay. All right. Okay. Next and the most important part is the stress and diffusion external force. And this is where different schools of thought come in. Those coming from mechanical or civil engineering, continuum mechanics, will call this an external force, and it's called the stress tensor, or the stress external force caused by fluid elements rubbing on each other, okay, and kind of compressing each other. But those from chemical engineering, they call this diffusion. Now, strictly from the perspective of Newton's second law, we had summation of external forces. And so, coming from mechanical or civil engineering, you might say like, yeah, this is just a force. But at the same time, its units are the units of diffusion, the same units of diffusion, which is really weird. And then when you do all the derivation, the result looks like a second derivative. It is diffusion. So which one is it? Who cares? The result is the same. And if you can understand both interpretations, then you are all better, okay? I am going to interchangeably call this stress diffusion, viscous stress. All of those words mean the same thing, okay? Because I'm going to present this as a unified theory, as a unified approach, okay? This is our final external force. It is a surface force, and a very complicated surface force. And it comes from these fluid elements rubbing and compressing on each other. So as they're transported, they're not penetrating each other. They're kind of touching each other, compressing so that they deform, so they exert a force, etc. However, I said they're not exchanging matter, but they are. As they rub on each other, they're diffusing information from one element to the other. Same for the control volume. Okay, so although this is a process resulting from forces, caused by forces, the result looks like a diffusion mechanism. It looks like diffusion, okay? And that's how we're going to interpret it. So these forces, they result in a process similar to diffusion. And remember, the same way momentum advected in all directions, momentum is going to diffuse in all directions. So x momentum will diffuse in ijk, y momentum will diffuse in ijk, and z momentum will diffuse in ijk. So we have three components of momentum diffusing in all three directions. Three components of momentum advecting in all three directions. 3 by 3, 3 by 3, okay? 3 by 3, we're getting there. Okay. Now we will use a specific symbol for this diffusion of momentum or this stress term. And we're gonna call it either boldface tau, okay? It's not a vector, okay? It's gonna be called a tensor, but we're just gonna call it boldface tau, or tau ji or tau ij, okay? Whichever, it doesn't matter, okay? And we're gonna refer to diffusion of momentum, the flux, the diffusive flux of momentum, or the stress forces caused by fluid elements, as tau ji. What does j and I represent? And I'm gonna follow my nomenclature. I know you've probably seen it as tau ij, but that's wrong. It should be tau ji, and I explain why. Now, it's a nomenclature, it's a convention thing, okay? So my convention here is that I is the component of momentum being diffused, okay? Because eventually I'm gonna write my equations as d rho ui by dt. Oh, I'm diffusing component rho ui. So in my nomenclature for diffusion, I always want I, the symbol I, to designate which component of momentum I'm diffusing, okay? And then what does J represent? J represents the direction it is diffusing in, okay? So again, tau ji represents the I component of momentum, could be X momentum, Y momentum, or Z momentum. There's only 3 options. Diffusing in the J direction. Now, this is not J unit vector. No, J is simply an index saying this could be either X, Y, or Z direction. Okay? So again, tau ji represents the diffusion of the I component of momentum diffusing in the J direction. Also, if our control volume is a cube, okay, this is the diffusion of the I component of momentum on a J face. Remember, we said an X face is a face perpendicular to the X axis, a Y face is a face perpendicular to the Y axis, and a Z face is a face perpendicular to the Z axis. Okay, so J would also represent not only direction, also represents which phase the momentum is diffusing through. Okay, this is going to become clearer and clearer as we do more examples. Another way you could talk about this, if you forgot J, I, J, just call it tau dc. D for direction, C for component. So if I tell you what is tau zy, you just write tau dc. Oh, tau zy means direction is Z, and Y means component, right? DC. So this must be the diffusion of Y momentum in the Z direction. Okay, we're going to do some examples now. If I were, for example, to look at only the X component of momentum, okay, so then I would fix the second index in tau ji or tau dc. I'm going to fix it at here. I'm going to fix it at X. Okay, so I fixed the component. I'm only looking at the X component of momentum and how it's diffusing. So I fix it at X, but I still have J variable because I'm diffusing the X component of momentum in all 3 directions. What are those 3 directions? There are 3 of them. I, J, X, Y, and Z, right? So therefore, then the total diffusive flux would be tau XX in the I direction, tau YX in the Y direction, and tau ZX in the K direction. Think about this. The second index is my component of momentum, okay? So you always see X at the last as the last index. Tau XX, tau YX, tau ZX. The first index is telling me in what direction it's diffusing. So tau XX, look at that. Tau XX is the diffusion of X momentum in the X direction or through an X face, okay? Tau YX is the diffusion of X momentum, but through a Y face or in the J direction. This is it. Tau YX is going through a Y face, and it's the diffusion of X momentum through a Y face. And finally, tau ZX is the diffusion of X momentum in the Z direction, okay, or through a Z face, okay? Now, it's not surprising that the diffusion of X momentum is a vector, the diffusive flux, right? Just the same way that the advective flux, remember, x momentum diffuses in three directions, x, y, and z. Okay, so it's still the x momentum component, but it's a diffusive flux vector, right? Now, its divergence is going to give us the net diffusive flux, okay? But all of these contribute to the x momentum diffusive flux. So think about it that way. The same way we had the x momentum advective flux, u rho ui plus v rho uj plus w rho uk. Right now here we have tau xxi plus tau yxj plus tau zxk. Okay? Eventually, we're going to sum all of those up along the surface or take their divergence, and then ijk will disappear and you'll get just a scalar contribution for x momentum. Okay? Now the same applies for y momentum and z momentum. And also don't forget that tau xx, each component, tau xx, tau yx, tau zx, they are fields. So tau xx changes from this face to the other face. There's a change of tau xx. It's still called tau xx, but it's different on the other side of the volume. Okay? So point-wise, it's changing, and it's also changing in time. Okay? Clear? Is this clear? Because nomenclature is going to get messy. All right? We have two things we're tracking now. Okay? And I'm getting you ready for tensors. Because I have three components of momentum, each diffusing in three directions. I have 3 by 3. Three components of momentum advecting in three directions. I have 3 by 3. Okay. Let's keep going. So now similarly, the diffusive flux of y momentum and z momentum, each one of them is a vector. Okay? Now for y momentum, you fix the second index. So you have tau jy. Agreed? Because you're fixing y, that's the diffusion of y momentum. And then the other index is going to pick up which direction it's diffusing in. Tau xy is the diffusion of y momentum in the x direction. Tau yy, diffusion of y momentum in the y direction. And tau zy is diffusion of y momentum in the z direction. Similarly, diffusion of z momentum, you're going to fix the second index at z, but it's diffusing in x, y, and z as well. So tau xz is diffusion of z momentum in the x direction. Tau yz is diffusion of z momentum in the y direction. Tau zz diffusion of z momentum in the z direction. Now when I say tau xz diffusion of z momentum in the x direction, does that belong to x momentum or z momentum? It belongs to z momentum. Okay? Because I'm diffusing z momentum. So if you use those words as you write your equations, you'll get it right. Because someone might say, well, x direction, isn't that x momentum? Isn't x momentum in the x direction? Sure. But a direction is just a direction. What I care about is which component I'm diffusing. So this tau xz and tau yz, tau zz, they belong in the z momentum equation, right? Because they correspond to the diffusion of the z momentum component. Okay. Let's start introducing a different notation as well. Instead of using x, y, and z, I like x, y, and z because they make me feel happy, and I can think of x, y, and z, right? They're easy. But also you can index using 1, 2, 3, where 1 is direction 1, typically x, or it could be r theta z, for example, could be r. Direction 2 is the second component in your coordinate system. So in a Cartesian system, this is y direction, and index 3 is your third direction, which is z in a Cartesian coordinate system. So if I use that notation for a Cartesian system, all x-related quantities have index 1, all y-related quantities have index 2, and all z-related quantities have index z. With that convention, then I can rewrite my x-mom component. So in this notation 1, 2, 3, my velocity field is u1, u2, and u3 instead of uvw or ux, uy, uz, okay? It's just u1, u2, and u3, where 1 is the first direction, 2 is the second, 3 is the third. And then in that notation, for xmom corresponds to component 1. So my second index is going to be 1, Okay, so my second index is going to be 1, talking about x momentum. And then my first index is going to change across all other 3 directions. So tau 11 is the diffusion of x momentum in the x direction, or diffusion of the first component of momentum in the first direction. Tau 21 is diffusion of first component of momentum in the second direction. Tau 31, diffusion of first component of momentum in the third direction. Okay? Repeat that. As you write the equations, as you derive them, I ask you a question, use words like this to understand. It makes an incredible difference. Makes it so much easier. Oh, what is tau 32? No, it's the diffusion of the second component of momentum in the third direction. That means it's the diffusion of y momentum in the z direction. Okay? Repetition is going to make you perfect with this. All right? We have 3, for each component of momentum, there's a diffusive flux vector, right? For each component. So Tx mom is the diffusive flux for x momentum. Ty mom is the diffusive flux of y momentum. Tz mom is the diffusive flux of z momentum. I haven't said anything about what tau is. It's just tau right now. It's an unknown. I'm not going to say anything about it for a while. We're just going to keep calling it tau. It's just a symbol to allow us to account for everything that's going on. Okay? So now that I have these individual contributions, then my x mom contribution comes. So if this is the diffusive flux in x for x momentum, I still need to integrate it. This is the diffusive flux vector. I need to integrate it, right, to get the full contribution. So this is pointwise at every point on the control volume. Okay? So now I need to get the total, and the total is simply that surface integral, the net diffusive flux. Remember how we did that with the balance equation? And what we did with the advective flux, we have the integral of div u rho u, div u rho v, etc. Same thing we need to do here for the diffusive flux. Remember, it was integral of div j, right? Or integral of j dot n ds when we did the balance equation. Same thing here. To get the net contribution of the diffusive flux, we need to integrate it over the surface of the control volume. So for x mom, that's the integral of the diffusive flux, x momentum diffusive flux, dotted with the unit normal. Okay, so that gives me scalars, and then I get a scalar contribution to the x momentum equation, which is a scalar equation. Now I want to express everything in terms of volume integrals, so this becomes div t, x momentum. Okay, and that is a scalar. Okay, t is a vector, divergence of vector gives me a scalar, and that makes sense because the x momentum equation is a scalar equation for x momentum. Okay, it's not a vector equation. Okay, it contains divergences of things in it, but they all are going to result in a scalar. Same thing for y mom contribution. T, the diffusive flux of y mom is this tau xy I plus tau yyj plus tau zyk. And then the net diffusive flux of y momentum is going to be that volume integral of its divergence. Again, this is going to result in a scalar value that is going to go in the y momentum equation, because the y momentum equation is a scalar equation for the y momentum scalar component. Okay? And then finally, the z mom contribution, you see by symmetry and by analogy. Again, you're fixing, this is the z diffusive flux vector, okay, for the z momentum. So if I tell you what is the z diffusive flux, what if the diffusive flux of z momentum, this is it. Or if we want to use stress nomenclature, this would be the force vector for z momentum. But I'm using diffusive flux. It's just a little more convenient from a chemical engineering perspective, okay? But these are also equivalent if you look at from a mechanical engineering or civil engineering perspective. This would be the force component, okay? This would be the force of x in x moment for x momentum, the force vector. Its divergence is going to give you a scalar, okay? But the force interpretation gets a little weird because it's a vector, and should I take only the x component of it? So stick with the diffusive flux. Diffusive flux is a vector. Its divergence is going to give me the scalar, which is the net contribution for each component. Okay, excellent. Concerns? Questions? Comments? Okay. We are ready. For what? We are ready to marry these forces finally into the right-hand side of each of these equations. Okay? So let's do it. For x momentum, that was my left-hand side, the accumulation and the advective flux, all in volume integrals. And that was equal to the summation of forces for x momentum. And this is a scalar equation. If this is not clear to you, make sure it is clear to you. Rho u is a scalar, div u rho u, although u is a vector, but its divergence is going to give you a scalar. Okay, so the result is a scalar equation for rho u, for x momentum. And fx momentum, that's also a scalar. That's only the x momentum contributions of all the forces. Okay, so what were those? Was the x component of the force of gravity, the x component of the pressure force, and the x component of the diffusion, the contribution of the diffusion flux. Okay, which is the integral of div tx. Okay, remember tx is tau xx, tau yx, and tau zx, and its divergence is going to give you a scalar, right? So when you plug these back in to the equation, where they're all volume integrals, and if this is true for any volume, then the integrands must be equal. The analogy I give, if I give you integral of f of x from a to b is equal to 0, whatever a and b are, then the only logical conclusion is that f of x equals 0. Same thing here. The integral over any volume of these things rearranged is equal to 0. Then the integrand must be 0, and then you can rearrange them, and then you finally get the differential form of the x momentum equation. Okay, and that's partial rho u by partial t plus div u rho u equal div of the diffusive flux of x momentum. We don't know what that is yet. We're getting there, but it just gives us the nomenclature, minus the pressure gradient in the x direction, plus rho gx, the gravitational contribution in the x direction, okay, for x momentum. Okay, so that's our differential x momentum equation. Same thing for y momentum. All you're changing is going from rho u to rho v now. So even if I just took the rho v, the differential form, and changed from rho u, look at this. So, okay, notice on this one how I'm just changing v, u to v. So I get, that's what's nice about these equations and their symmetry. So here I simply substituted u by v, and then here also rho u by rho v. Here I put y mom, and this is dp by dy, and this is gy. Okay. And finally, we have the last momentum equation for z momentum, rho w. So you have this partial time derivative, change in time, and then advective flux, diffusive flux, pressure gradient, and gravitational force term. Okay, together they give you the full set of equations. So far, yes, these are for fluid flows, but they're actually more general than a fluid. Okay, so let me expand them first. So if I expand this and you keep them all in conservation form all the time, keep everything inside the derivatives, okay? That's the right way of doing it. So if you notice, I'm expanding these, and you should do this exercise. I'll probably assign it today for your homework. So I'll give you these equations in the equation sheet. So the one I told you earlier today that I uploaded contains these equations, okay? These equations in stress form, in the diffusion tensor, in the diffusion form, tau xx, tau xy, etc. But you expand everything, right? D rho u by dt, and this guy is, for example, for x momentum, this guy is div u rho u, right? du rho u by dx plus dv rho u by dy. Keep them in that order, please. Don't change the order, so you know what is advecting, what is being advected. And then this guy is super important to distinguish what is the diffusive flux vector for x momentum. And once you take the divergence, it becomes a scalar. So this is proof to you that, yes, although this equation has vectors in it, but the divergences knock out those vectors and turn them into a scalar. So this is a scalar equation for x momentum. This is the scalar equation for y momentum. and this is the scalar equation for z momentum. Okay. Now, we didn't say anything about the diffusion tensor. Okay, we said nothing about tau ji, tau ij, and whatever. Okay, or the diffusive or the stress, whatever you want to call it, stress tensor, viscous stress tensor, viscous diffusion tensor, all of those. We didn't even say tensor. Don't say tensor. So the viscous term or the diffusion fluxes, we didn't say anything what they contain. We kept everything as tau xx, tau yx, tau zy, etc. And I'm not going to say anything because what is so cool about these equations is that they don't apply actually only to a fluid. They do apply to any continuum material that's deforming and that's in motion. In fact, they do apply to a solid as well. If you're looking at the individual solid particles as they deform when they are subject to a force, right? So I'm taking, I hope I don't break it. So I'm taking this, see how it's deforming, right? See how it's deforming. What governs this deformation is these equations, okay? They are called the Cauchy momentum equations, okay? Augustin Louis Cauchy, I think his name is. He's a great mathematician. So these are the equations of motion for any continuum material. What you would have to specify is what that tau looks like for the different materials that you're dealing with. For solids, tau looks very different than for fluids or for gases, okay? It looks very different. For a solid, you might not, the gravitational term might not matter for small objects, and the pressure force doesn't necessarily exist. So it would be just a source term. But these are the general Cauchy momentum equations of motion. They are more general than Navier-Stokes, more general than the gas dynamics equations, more general than any solid mechanics equations. Because what is different, if you want to apply these to a solid, then you specify what tau is. And it's going to be different than what tau is for a Newtonian fluid or for a plastic fluid or for a fluid that like cornstarch or your toothpaste. Tau is going to be very different, okay, for all of these different materials. But they all have the same set of equations. This is so cool. This is actually beyond gas dynamics. These are the most general equations of continuum motion. Any continuum you have will obey a form of these equations, okay? The source terms will be different. There might be other source terms, but the most important piece is that that diffusion term, the tau, okay? Now, before I go into what tau means for a fluid, because we're only focused on fluids here, I want to take a detour and force you with me to simplify these equations so we can write all of these three equations as a single equation, okay? And in the process, demonstrate to you that the only way we can do this is by using tensors. Okay, so now my question is, can we improve on these equations? Can we make them a little simpler, so a little more concise, so that instead of having to write, let me adjust this for a second here, instead of having to write every time three different equations, can I write all of these as a single equation? And it kind of makes sense because rho u, rho v, and rho w, they are components of one vector, rho vector u, right? Because if I have rho ui plus rho vj plus rho wk, I can write all of those as one vector, rho u vector, right? What about the other terms? Okay, let's figure this out together, okay? So the first step, I'm going to take these equations and just argue like I argued. If this is the equation in the I direction, right, that's the x momentum component, so this equation must exist in the direction I. And if I add to it this other equation and make it in direction j, and I add to it this third equation and make it in direction k, now this ijk can just be distributed across all of those terms. So what I would have here is d rho ui plus d rho vj plus d rho wk, correct? And that is what? That is my momentum vector, right? Agreed? So d rho u vector by dt is d rho ui plus d rho vj plus d rho wk. Agreed? No, any magic going on here? Nothing magical, right? Okay, what about the pressure gradient? dp dxi minus dp dyj minus dp dzk. That's what? Well, that's the pressure gradient, grad P, right? I already have that. In fact, we started with that when we did the integral of the pressure force, right? It was grad P. Okay? What about gravitational force? Well, we also started with a vector force. We ripped it apart, but now I want to combine it back. So I have rho gxi plus rho gyj plus rho gzk. That's vector rho g. Okay? Okay, what about these other two terms? They're weird, right? They are weird. Are they? Well, think about it. Div u rho u is a scalar. And that scalar, although it has a vector in it, is in the I direction. But inside it, there's ijk, but those ijk are in the I direction. That's so weird, right? That's so weird. Same thing for div u rho v. There's ijk in u and in div, but all of this term, this entire term is in the j direction. Although inside it, there's ijk and dotting with each other, right? It's so weird. How can we write this? How do we write this? How the heck do we write this? I'm going to give you how we write it, and then we're going to rip it apart to make sure it gives us exactly what we want, okay? This is written as div u vector rho u vector, okay? So this u vector already existed at vectoring velocity, already existed here, so I'm not changing anything, okay? And this div already existed here, okay? It's right here. But rho u, rho v, rho w, they're multiplied by ijk, and I'm claiming that the correct way to write this is like this. Div u, rho u. So now I have a divergence of two vectors next to each other. That's weird. Have you ever seen this? No. Maybe you've seen it, but if you haven't, that's cool. I have the privilege to letting you see this for the first time ever in your life, right? There's always a first time. Now, what about the diffusion thing, right? There's divergence of a vector. So it's a scalar in the I direction, scalar in the y direction, scalar in the k direction. But there's vectors inside it. There's div and t, right? So how do we write this? I'm also going to write it as simply as div tau, okay? Now, this tau is my tau ji, right? And we're going to figure out how to combine them together. And there's going to be a curse of dimensionality coming at you in the next slides, okay? But it's going to elevate your thinking because this single equation, I claim this single equation represents all of these equations which have so many terms, okay? And trust me, when you are doing modeling on Navier-Stokes or fluid mechanics, this is the equation you want to deal with, because it's so easy to do operations on this vector equation to calculate things like angular momentum, integrals, getting vorticity. It's easier to work on this single equation than work through the different individual equations, okay? But we need to now understand so the first term, the pressure gradient, and the rho g terms, they're clear, they're easy. Agreed? We know what they mean. But we have two new terms. This advective flux, it's weird. It has u, rho u in it. We've never seen that before. Two vectors, are they multiplied with each other? As far as we can tell, no, because the multiplication, we defined it as either a dot product between two vectors or a cross product. Those are the only two multiplications we know between vectors. So this is going to be a new type of multiplication of vectors, u, or vector A times vector B. It's a new multiplication next to each other. So we're going to start by understanding this term first, u, rho u, and then we will go after this tau. I'll give you a 3-minute break, Okay, go grab some water, stretch your legs, and then we can dig into this, okay? I'm actually gonna go get some water because I spoke a lot. No, I'm taking a break. All right. All right. Can anyone check on Thomas? Is he okay? He's probably in the lab. Tonight, I will take you on a journey. There's these long form YouTube videos that on physics and like relativity or history. They're like 2-3 hours long, and you have this like deep narrator voice. They'll like knock you flat out. Like within 5 minutes you fall asleep. You're listening to them. They're really cool, and then you wake up in the middle of it, and there's like a discussion about black holes, and they're gonna swallow everything. And so I feel like I'm doing the same here. Okay, we ready? Hello? Let's resume. So next, what I want to go after is the meaning of these two new terms that were not too obvious to us. This div u, rho u, there's two vectors stacked next to each other. And then there's this tau, which was tau ji. There's like three components of momentum and three directions. So we want to talk about all of that. But first, I will start with u, rho u, to try to untangle what it is and what it means, and that it's not such a mystery. And in the process, we will define a new vector product. So far you know dot products and cross products. We will define a new product where you just put two vectors together next to each other without a symbol between them. All right. So what is this object called? It's u vector rho u, right? So u, I know this is the advecting velocity, agreed? And this rho u, that's what is being advected, okay? And that's the momentum vector, rho u, rho v, rho w, right? That's momentum per unit volume. So I'm going to put parentheses here next to this so I can separate. I can always keep track of advecting velocity field and information being advected. Now, there's a problem here because u is a vector, u, v, w, and so is rho u. This is rho u, rho v, and rho w. So it's a vector multiplied by a vector. We don't know what that multiplication means. So for a moment, I'm going to call this m for momentum, lowercase m. That's why I chose to use capital M earlier, just because of this stupid slide here. So I chose mass as capital M because I want to use lowercase m for momentum per unit volume. So I'm going to call this m for a minute to distinguish u and u. So I'll have u times m, okay? And m is simply just a vector, mx, my, mz, and that corresponds to rho u, rho v, rho w. It just didn't do anything except change nomenclature for a second. Okay, so I'm going to call this m, all right? And there are several ways to think about this. So we know the answer, right? Because we know the individual components of the momentum equations, right? So we know how to untangle this. We just want to wrap our head about this new nomenclature that I'm using. So there are several ways to think about this. We're going to go at this by component of momentum, okay? So when we looked at the Navier-Stokes, we looked at these x, y, and z components equations separately. So for x momentum, I know I'm transporting mx, right? So my um vector should give me u at vectoring velocity times mx, and we know, we derived this earlier, that's going to be umx, vmx, wmx, or u rho u, v rho u, w rho u. And that's a vector, right? Before I take the divergence, that's still a vector, umx. And then same thing for y momentum, I'm at vectoring my, so this would be u times my, u vector, right? And that's u rho v, v rho v, w rho v. We know this, we've seen this. And finally, mz, that's the z momentum. So umz, u vector, it's transporting mz, z momentum. That's umz, vmz, wmz, or u rho w, v rho w, w rho w. Okay, great. I'm gonna move this here and go back to u rho u. Okay, what is going on here? I have these three components of momentum. Each component, we're gonna agree that they are in different directions. So this would be in the I direction. This is the component for x momentum, right? In the I direction, in the j direction, and in the k direction. And each direction has I, j, k components. So you can look at this either column-wise or row-wise. Column-wise, u rho u, u rho v, and u rho w, they are the advection in the I should swap. Sorry. So let me swap this. See, even I can get in trouble with this. Let me swap this. Okay. I will update the slides later because they're going to be everywhere moving forward. So you can see there's a combination of direction and component. Okay, there's a combination of direction and component. Let me actually fix this just right now. Okay, please. So this is component, my apologies. And this is direction. Okay, and this is gonna propagate everywhere. One second, so I don't confuse you. Okay, perfect. Okay, so that's x momentum component, y momentum component, z momentum component. But then being advected in the I direction, j direction, k direction. Okay, so think about this. I have this u, rho u quantity has all of these 9 entries in it, agreed? Because if I account for all the different directions and components, I'm gonna get these 9 quantities out of this u, rho u vector. So this u, rho u vector is a quantity that has 3 directions and 3 components in each direction. Or 3 components and 3 directions in each component. Okay? In this form, this u, rho u, this multiplication of these 2 vectors is called a dyadic product. A dyadic product, it comes from the word dyad, and that's when you put 2 vectors, multiply them next to each other. It's not a dot product or a cross product. Okay, it's just putting 2 vectors next to each other. It's called a dyad. But in this case, it results in 9 entries. A dyad in 3 dimensions results in an object that has 3 directions and 3 components per direction. Okay? It has 3 directions and 3 components per direction for a total of 9 entries. A total of 9 entries in that quantity. When you put 2 vectors next to each other as well, you're multiplying them without doing a dot or a cross product. This is also called an outer product of 2 vectors. It's also called a tensor product, and we will know why in a second. A dyadic product is simply the operation of placing 2 vectors next to each other. If I place 2 vectors A, B, or U, U, placing them next to each other, automatically you should deduce in 3 dimensions. This results in 9 entries. There's 3 directions and 3 components per direction, okay? This is also called a tensor. Okay? This is also called a tensor. Think of a tensor as a way of accounting for multiple components and multiple directions. This advective flux tensor, this advective flux quantity, this weird object, has 3 directions and 3 components, and they all are connected to each other. They're not separate. You're not just taking temperature, pressure, density, and combining them in 9 different ways. No. This is very specific for special vectors. So you're transporting a vector by itself or with another vector. It is going to result in a tensor. Okay? It's going to result in a tensor. You have 3 directions and 3 components per direction. And this makes sense because I have 3 momentum components, each advecting in 3 directions. Together, there's 9 total entries that describe this entire advective process. And we call that a tensor. It's simply a mathematical object, that allows you to account for 3 directions and 3 components per direction. Tensors are more general, okay? They're much more complicated than this limited application. So we're going to keep it at that, but I'll define it. The rank R, tensors are defined purely by their rank, okay? The rank R of a tensor determines how many entries it has, very simply, okay? And R could be any integer from 0 to infinity, okay? Assume if we live in a 3-dimensional world, which might not be the case for string theory, for example. They might have, their tensors might be 27-dimensional, okay? And they have a rank on them. That's a different world, okay? For us, we live in a 3-dimensional world. A tensor of rank R in a 3-dimensional world has 3 to the power R entries in it, okay? Don't call them components yet, just call them entries, okay? Has 3 to the power R components in total. So a tensor of rank 0 has 3 to the power 0 entries, which is 1 entry, and that's a scalar. A scalar, a number, is simply a tensor of rank 0. A tensor of rank 1 has how many entries in it? It has 3 to the power 1 entries. It has 3 entries in it, and that would be a vector. A vector is a tensor of rank 1, just simple definitions, right? Is 3 to the power 1 entries. And finally, a tensor of rank 2 has 3 to the power 2 entries in it. Okay, it has 9 entries in it. And therefore, our advection tensor is a tensor of rank 2. It has 9 entries in it, accounting for 3 directions and 3 components per direction. So that's 3 by 3. It gives you 9 total entries. And you will see that many people write this in matrix form. Okay, but that's wrong and confusing because this doesn't generalize for tensors of rank 3 or higher. You can't write them as a matrix, okay? You have to write them a cubical matrix and then in a hypercube. It doesn't make sense. And second, it's confusing. What do you choose to put in the rows and what do you choose to put in the columns? Do I put the x momentum, y momentum in rows and then x and then direction in the rows, or the other way around? You will see people mess things up using this form. I do not recommend it. Don't do it. Don't write tensors in matrix form. I know it seems to make life easier, but it doesn't once you get to do divergence of these tensors, because in the end, we're going to do the divergence of this tensor. How the heck do you apply the divergence to a matrix? Okay, this is where people get confused. They get away with it because this matrix representation is symmetric along the diagonal. So you will see, and that's the only reason that people get away with it. You will see that rho uv here is equal to rho vu, and rho uw here is equal to rho uw, rho wv is equal to rho vw. And so however you arrange them, it's going to give the same answer numerically. But once you go to non-symmetric tensors, this will mess things up. Don't write it in matrix form. Don't be tempted to write it in matrix form. And when they write it in matrix form, ask them, why did you choose to put them in rows rather than columns? They go, well, it's symmetric. Well, what if it's not symmetric? It's wrong, okay? And it's ambiguous. All right. So how do we make sense? How do we write this? How do I express this in more elementary form? Like, it's still weird. U rho u. How do I take the divergence of u rho u? How do I express this? How do I put all of these quantities in one line, in one form? How do I do it? So you could say, okay, I'm just gonna take them in the one direction at a time and then list the components like I did here. Okay, but there are a few cleaner ways to do it. Okay, I'm gonna present you with two ways. The first one is using a dyadic form. Okay, and the second one is using tensor index notation. Okay, the dyadic form is the one that I personally like because it's very, very clear and unambiguous at all. But some people haven't seen it before. So, you know, feel free to not use it if you want, but to me, it's always the best, the easiest way for me to write these with full clarity. And the idea is to simply express this u and u rho u by expressing each vector in terms of the unit vectors I, j, k, and then using dyads on I, j, and k. Okay, and then making sense of that. So if I were to write u rho u as a dyadic product or a tensor product, I would simply expand the first vector, which is u, that's ui plus vj plus wk, and then do the tensor product or the dyadic product with the other vector, which is rho ui, rho vj, and rho wk. Now, what I'm going to do next is simply distribute as if I'm just doing a distribution of product. I'm going to distribute ui across all of these terms, vj across all of these terms, and wk across all of these terms. I'm going to get terms like ii, ij, ji. Those are dyadic unit vectors, and that's fine. But I have at least an interpretation for them. So here's I'm going to do this. ui distributed across all of these terms is going to be u rho u, is going to be ui rho ui. And I'm going to rearrange, so that's going to give me u rho u I. And then ui times rho vj is going to give me u rho v ij, because the vectors are going to move to the side, right? Okay, so what I'm doing here, so the first one is this guy, that's this guy. The second one is going to be this, ui times u rho v. And the third one is ui times rho wk. It's going to be u rho wik. Okay? Now, this immediately makes sense to me. Why? Because the first index is the direction, the second index is the component. And then I can look at u rho w without looking at the unit vectors. What is u rho w? It's the advection of rho w by the u component. Correct? But then look at the unit vectors. They're I, k. That makes sense. K is the z component of momentum, rho w, and I is the u velocity component, right? And so that makes much, much clearer sense to me. And then I do the same for the remaining components, and we will spend some time on this. So the remaining components, I'm going to distribute vj across all of the others. And I get v rho u ji plus v rho v jj plus v rho w jk. Okay, so let's stick with v rho u, for example. What is v rho u? It's the advection of rho u using the v velocity component. But then look at the unit vectors. They're ji, which is consistent. J is coming from v and I is coming from rho u. So v rho u ji is enforcing the idea that v is the advecting velocity that corresponds to j, the first unit vector. Rho u is what is being advected, so that's the second unit vector. Does this make sense? So whether I have those two dyads, ji or not, I can either way tell and enforce the idea that this is indeed the advection of x momentum by the v velocity component. Is this clear? This is only notation. Like, oh, ij, I'm gonna freak out. Just, it's a dyad. Okay, ij is telling you something about what direction and what component is being advected. So more specifically, I'm going to take a component, w rho v, for example. W rho v has a dyadic product, kj. And this is enforcing the idea that K corresponds to W, which is the direction in which momentum component is being advected. And J is telling me which momentum is being advected. Now, remember what my nomenclature was for tau Ji. I said the second index is the component of momentum being diffused, and the first index is which direction is being diffused in. Same thing for the advection tensor. The second index or the second unit vector is going to tell me which component is being advected. The first index or the first unit vector is going to tell me which direction it's being advected in. Okay? Now this is again the advection of y momentum, rho v, in the z direction using the w velocity component. Okay, great. So how do we compute now the divergence of a tensor? And this is where it gets really, really easy using this dyadic notation. Okay, now I want to do div u rho u. We know the answer already from the equation, but what does the divergence of a tensor, what should it return? What do you think it should return? We know that the divergence of a vector returns a scalar. What does the divergence of a tensor supposed to return? Remember, the result of this should give me the three components, the advective flux for each component of momentum. There are three of them. So what should this return? A scalar?
Should give us
a what?
It should give us a quantity of each vector in their direction.
It should just simply return a vector. The components of this vector, the first component contributes to x momentum, the y component contributes to the y momentum, and the z component contributes to the z momentum. And I'm going to prove this to you. So, for example, we know from the previous equations that div u rho u, remember when I went back to the equations and put I, j, k on the right hand side, this is what this should return. If my math and my nomenclature is correct, div u rho u on the dyadic product should return div u rho ui plus div u rho vj plus div u rho wk. Each one of them is a scalar, but at least this one contributes to x mom, this one contributes to y mom, and this one contributes to z mom. Now what is this? This is a vector. On the left hand side, I have the divergence of a tensor. This is divergence of a tensor, and this is a vector. So then, indeed, the divergence of a tensor should return a vector. And specifically, there's a definition that I'm going to call you upon. The divergence of the advective flux tensor returns a vector whose components correspond to x, y, and z momentum net advective flux contributions respectively. So this divergence of the tensor, of the advective tensor, returns a vector. The first component contributes to the x momentum advective flux. The second component contributes to the y momentum advective flux. And the z component of this vector contributes to the z mom convective flux. Okay? You chose to go to grad school. You have to learn this. You have to know this. As a chemical engineering PhD or master's, you might never use this ever again. But once they see PhD chemical engineering, you should at least know what a tensor is doing, what the divergence of a tensor gives you. Okay? Yeah, it's a lot to wrap around, and I spent sleepless nights trying to make this together, and I still screw up, right? And I just did with direction and component. But if you follow the steps I'm going to give you, I'm going to give you to compute the divergence with the dyadic form, it's going to all make sense, okay? Please review these. It's not going to get easier. It will continue getting harder, okay? It will continue getting harder. Please review these before next week, and have a good weekend. Godspeed. We will resume next week, okay? Thank you very much.